Hello everyone, welcome back to day 32 of Coding Every Day. Today is Sunday, February 16, 2025 at 1:22 p.m. So recently I've been doing these graph problems here, so I will continue today with course schedule. So I haven't really looked at this one. I looked at it a little bit, but not too in depth. So let's get started here. So you're given an array prerequisites where prerequisites of I is AB. Indicates that you must take course B first if you want to take course A. Okay, the pair 0, 1 indicates that you must take course 1 before taking course 0. There are a total of num courses you're required to take labeled from 0 to num courses. Okay. All right. So this is with, like in graph theory, I think this is an adjacency list. So we can build our graph based only on these prerequisites. So this will be an edge. So I guess how we could do it is like, to take A, you must first take B, or we could have, I don't know if it's better to have A pointing to B or B pointing to A. It should probably be like this. So first you travel here and then you can go to this one. So we'll have a course and then all of its prerequisites. Well, I guess. So let's say to take course A, you first must take course B and C. Then would it look like this? Okay, and then return true if it's possible to finish all courses, otherwise return false. Okay. So let's run through some examples and I'll determine how I want to build the graph. So here, prerequisites. So there's two courses, course 0 and course 1. And you must take course 1 before you take course 0. So we have it like this. So 1, should we have it like once you take course 1, you unlock all of these courses? Probably not, because there might be several other courses that you need. So I think it should be like this. So these are all the prerequisites. And once all of these are filled, then you know you're good. All right, let's look at another one. So if you have 0 is dependent on 1 and 1 is dependent on 0, then you can never, you have a graph that looks like this. So I think this problem can be kind of simplified into just a cycle check. Like you just want to check if there's a cycle in the graph. So if you have like this, so if course 1 is dependent on course 0, course 2 is dependent on course 1, and course 0 is dependent on course 2, you can never, and let's say there's another course here, 5. So you can take course 5 because it's not dependent on anything. And then you can't take course 0 because it's dependent on 2, and you can't take course 2 because it's dependent on course 1. You can't take course 1 because it's dependent on course 0. So whenever we have a cycle, I think the answer is false. If we don't have a cycle, for instance, if our graph looks like this, let's say 3, then we would be able to take all the courses. We'd start here and here and here and here and here. Also, another thing is we have to make sure, so it could be like disconnected. So there could be like another, like course 5 depends on course 6. So let me stop saying 5. Course 6 depends on course 7 as well. And then it's like two components of a graph that aren't connected. This would still be possible. But if there's like a cycle in this one, then it would not be possible. So we just have to check every part of the graph and make sure there is no cycle. So I don't have how to do that memorized off the top of my head, so we're going to have to intuit it. But first, let me build the graph. So I want it to be a course and then all of its prerequisites, I think. And then what we can do is start at the course that has no prerequisites. Or should we do it like a course and then everything it leads into? I think I'll just do it like this. So a course and then everything that it leads into. And then, or maybe I need it. Because if I have the graph like this, I don't think it actually matters which way you have it. Well, it might be useful because you need to know what, you need to know if it has any dependencies. So you need to look at its in degree. I think what I'll do is just label it like this. So the, like how I have the arrows drawn. So it'll be a course and then well, let me think. So if I reverse all the arrows, so it's that. So if it's like this. I don't remember how the arrows were. Okay, so if I instead do like the orange arrows, like this, there's still a cycle either way. And this would be like A to B, whereas the purple arrows are B to A. So if 0 is dependent on 5, then you point to its dependencies. Okay, so I'll just do it like that and see if I can make some inferences. So we'll have a graph. For prereq and prerequisites. I'm just going to copy it. Okay, I did it right. So prerequisites is, so prereq is a list containing 2 elements. So we'll say AB equals prereq dot. Can we just do that? So if I have, I'm just going to test that out. So if I have a list 0, 1, can I say AB equals, no, that's not going to work. I think I can just say it like this. That should work. Okay, so now we want to say, and so we want to map A to B, right? So if A not in graph, then graph of A equals empty list, and we want to say graph of A dot append B. I wish they gave larger examples. Let me just make sure this is working. So 0 is dependent on 1. And then here we have 0 is dependent on 1 and 1 is dependent on 0. Okay. So then, so I'll say build dependency graph. And then we want to just check for a cycle. So check for cycle. So if there, so first of all, how to check for a cycle. I don't think breadth first search or depth first search matters. So I'm just going to build a graph. Okay. So if we depth first search, we have, let me draw it a little closer together. So if we have A, B, C, D, like this. Okay, so within our stack we have A. Stack. So we have A, and then invisited. And we add A to visit as well. Okay, so then now for every neighbor, if it's not invisited, so this is invisited. So we add it to the stack. Well, first we popped that. And then for every neighbor, if it's not invisited, we add it to the stack. So now we have B. And then, okay, then we pop B from the stack. And when we added it to the stack, we also added it to visited as well. Okay, so then we pop B from the stack. Is it just as simple as if it's invisited already, then you know it's a cycle? Okay, so B, we pop B from the stack. And then add its neighbors to visited and the stack. So C and C. So it's invisited. So then we pop this, add its neighbors, D and D. And now for D, so D's neighbor is already in visited. What if we have something like this though? So if we have E there, and let's say our DFS takes us this way, and let's just say because B, when we're here with B, we would have added E to the stack. And to visited. So E would be in the stack, and then C, and then we popped C. And then it would have went down there. So after we're done with C and it doesn't add anything, well, so this is where it gets tricky, is because we popped C and then also would have added E, but because E would have had to be invisited. But since we explored E twice from two different ways, then that has to mean... Well, in this case, there's actually no cycle. Like, if we get rid of this arrow, here there's no cycle, and you would be able to complete these courses, because you would go E, and then you can do C, and then you can do D, B, and A. So there's no cycle, but we do visit E twice. So we need like a... I wonder if this is why they have like the colors in graphs, because there's almost 3 states. There's like there's in the stack and in visited, but there's also like a fully explored set, which is after you pop it from the stack. Because once you pop it from the stack, if you re-go to it, so let's say our DFS took us this way. So if it took us this way instead, so our stack would be, so A would go to B, and then when you pop B, we would add C and E. and fully explored. So I'll just say like explored. We've popped A and B. But in visited is anything that's in the stack as well. So it would be A, B, C, and E. So then E would get popped, so it's fully explored. Okay, and then we're going to visit it again. So that doesn't necessarily mean there's a cycle. So how can we detect, for instance, if there's an edge here? Okay, let me think about this a little differently. Let me just try to intuitively first understand as a human how I know there's a cycle, and then I can try to like figure out the algorithm for it. Okay, so we visit here, and then here, and then here. And then we go back, visit here, and then here. So even though I'm visiting something that I've already explored, I know it's not a cycle. Why? Why do I know it's not a cycle? Because it ends here, like it doesn't go back. If we were to go to B, I wonder if you could do like breadth first search, if that changes anything. So if you go here and here first, no, because then you would see E. Okay. Well, yes, we have explored C, but or E. But I'm thinking there is a distinction with B. So if we revisit B, that's something that led to C. So if we revisit anything in our current like depth first search, so if we visit anything in our current path before we backtrack, because if we backtrack to C, for instance, now exploring D again doesn't really matter. The same way, so if we explore it A, B, E, if this went back to E or A, it would be a cycle. But when we backtrack to B, we don't really care about if we visit E again, because there could just be like this. We care about if we visit A again. So it looks like every time you backtrack, the nodes that if you visit would be considered a cycle gets shortened. So if we have like A, B, C, D, E, okay, so if we go to C from A, B, C like that, there's two nodes that if we visited them again, we would know it's a cycle. And then let's say there's like another path this way. So let's say we explore this path, F, G. So if we explore this path, we would know that at this point, anything, so we haven't backtracked once yet. So we know that if we hit any of these nodes, it's a cycle. Once we backtrack back to this C and we start exploring other neighbors, it doesn't matter if we hit F or G anymore. So like this would not be a cycle, for instance, but this would be a cycle. So we have to keep track of the nodes that would put us at danger of cycling. And when I say that, I mean, if we visit these specific nodes, we know that there's a cycle. So in our first run of the DFS, if we visit any of these nodes again, it's a cycle. But then when you backtrack to C, it only goes to these nodes now, would be a cycle if you visit them again. So we need to keep track of those nodes and somehow know, like when you backtrack to D in the stack, for instance. So you would have like A, B, B, C, and then C connects to D and F. So we would have like, I'll call it like cycle nodes or something. So it would be A, because that's where we start. And then B, so we just keep adding C, F, G. And then once our stack just has D in it, because remember it would have had DF when we explored C and then we popped this. So once we pop this, we should remove everything that led to that. So I don't know if there's a way to do that or not, but maybe what we could do is in our stack we could have also the parents. So in our stack we could have CD and CF like that. So at the moment when we pop CF, okay. Let me try that technique, but from the beginning. So we're going to have A just in our cycle. So it'd be like A, and then we'd have A that came from B. So A with, I guess we'll say B with parent node A like that. And then we have C with parent node B. And then we have F with parent node C. And then we have G with parent node F. Okay, so then in our stack, when we pop D with parent node C, I don't know how I'd implement this, but we would know that anything after C doesn't count, like in our cycle. Like these two wouldn't, but it's not going to be sorted or anything like that. I know there's definitely just a way to do it like pretty easily, but I think this is still good to try to just spend time thinking about it, and then once I eventually either figure it out or look it up, it'll just click more with me because I spent this effort trying to figure it out myself. So this makes sense to me, but programmatically, I don't know how you'd implement this. I was thinking, I had a thought like maybe if you encounter 2 visited things in a row, but I don't know if that's true either, because let's say our DFS takes us this way, and then we go here, and then we encounter B and then C, and there's no cycle here. I think there's different types. Oh, okay. I think I have something. There's different types of visited. So I think it's like you can't mark somebody as a cycle node. Like if you visit this node, it will be a cycle unless all of their children have been fully explored. Perhaps. So in this example, A, like A has all of its children have been popped from the stack once we pop B. So we know A is like in the danger territory of being a cycle. So A has B. So the stack is A. So when we pop A, then we add B to the stack. Okay, so I think it's the moments when we pop B that A becomes dangerous, only because B is its only child. So if we had like X here, A isn't considered dangerous until we pop both of these from the stack. Or does that not make any sense? Because if we explore like everything with B, you just have to keep track of everything you've seen so far. But it gets tricky with F and G. Because if F and G go to D, then that's totally fine. And if E goes to G, well, in this case it would be a cycle, but if you have it like this is also fine. Even though, but we've already seen G. We encounter G. So this is, so I need to figure out when, so if we see a node again, so there's two things going on. So we have something like this, and then we have another graph which looks like this. So we need to determine when one is a cycle and when one is not. So in both cases, we see something that we've already visited. So here, if we do it like that, so if we explore A, B, C, and then C, we see C twice, even though there's no graph. Here, we see A, and then B, and then C, and then A again. So we've seen A twice. And so here we saw C twice, and here we've seen A twice. Obviously, I'm looking at like the in and outs degrees as well. So for instance, this node has 2 in degrees, whereas here every node has 1 and 1. I don't know if that's the way to do it. I don't remember learning that. I definitely have learned how to detect a cycle before, but I don't know if you use that. I think it's something to do with there's different states of every node based on how much you've explored it. And if you So A goes to B. So here, there's this other line. All right. Okay, so the cycle in this graph is here. Maybe I could put it like this. Okay, so A. So let's make colors. So we'll say like red is fully explored and orange is like we're still exploring it. So A, we fully explore it. And what I mean by that is all of its, I don't really know what I mean by that. And then, so orange, this one I think is partially explored because we don't go down all of its branches yet. So if we visit a red node, so for instance though, even if we had a node here, let's say G or something, this would be orange, this would be orange, and this would be orange. But we still know that there's a cycle right here. Like as soon as we get back to A, we know there's a cycle. It's as simple as, it's literally as simple as if you've seen something in your current like loop without backtracking, then you know that you have seen, that you know there's a loop. So if you go like here, okay, let's say we have E here. Okay, so let's say our first one is here. Then we backtrack to D. So then we just have to somehow know how to remove everything that was explored here. And then we go to C, and then we find A, which is in our special group. So I just don't know how I would remove like all of this stuff. Because, okay, let's say we have F, and then it goes like this. So in this case, we need to know that there's a cycle here. So it's in our current traversal. If we go here and then backtrack to here, yeah, like if, so in this case, when we backtrack here, we have to remove G from being dangerous, because if we encounter G again, it's fine. If we encounter any of these, it's not fine. So I don't know how to do that easily, because what I could do is when you, so you know when you backtrack, when you pop something from the stack that belongs to the same parents that you, like your previous parent. So here, G belonged to C. Sorry, G belonged to C. And then when we pop H from the stack, H also belonged to C. So we have to remove this whole area from the list, from like the dangerous nodes. Is there a more like clever way to do that? Like, can we keep track of, oh, maybe what we could do is have a set, So maybe in the stack, we could also keep a set. This doesn't seem very memory efficient. But let's say at every time we add something to the stack, we keep a set of what we've seen at that point. And we constantly update it every time we pop. So so when we add B to the stack, we also add the set A. And then we pop from B, and then we add to the stack D with the set AB, and we add C with the set AB. And then we pop C from the stack. So then we add to the stack G with the set C, A, B, and H with the set C, A, B. And then when G is a dead end, then we pop this from the stack. So even if we encounter G, it's not in our dangerous set. Okay, I think that would work. So basically, within the stack, we also store like a danger list. We reset visited every time, I guess. Now, would this would this still functionally work as a DFS? Because when we go, so when we go back to H, well, I guess C is not coming back. So when we go back to H had CAB. And then we encounter G. So would we then add G to the stack with CABH and then pop it again? I don't know if you need to do that or if that will cause an infinite loop. CABH. G. So G has CABH. And then that would die and add nothing. Okay, and then we would go back up the stack. So those all died. C died. So we go back up to D. D with AB. So now if we encounter C, H, or G, it doesn't matter. The only ones that matter is this one. So then we would add E. Would we add C to the stack again? Hopefully not, because we've already explored C. Right? Like, it doesn't actually matter. Or does it though? So my question is, do we have to add C to the stack again with this new set? Because if there's a node here, okay, let me simplify the examples. That was useful to me in getting this set idea. So if we have A, B, C like this, say D. Okay. So A gets added with an empty, well, I guess with just A. So the only thing that we don't want to run into is A, and then that would give us, a loop. Okay, so then we add B and C to the stack. So let's add C first with A in it, and I guess C in it as well. And let's add B with A and B. Okay, then we pop from this stack and we add C with A, B, and C. So these are two different states that we've reached C in. Okay, and then D, so then we'd pop this one and say D equal, like D is A, B, C, D, and then that one gets popped. And now we'd add it again without the B. So it'd be like D, A, C, D. And then that we'd never run into it again. So my thoughts was, what if we DFS this way first? Would that cause an issue? So we would have A. I'll just do parentheses so it's easier to draw. And then we get C with AC. And then, well, actually, we'd have A. Okay, so there would be B with AB in the stack, and then we'd have C with AC in the stack. And then we'll pop this one, and that would give us, so D with ACD, and then also it'd give us B with ACB. Okay, and now when we pop from this, when we explore this person's neighbor, this node's neighbors, it would be C. So we would see that it can't explore C because C is already in its visited set. So in that case, we know, we've identified there's a cycle. So this would work. I just don't know if it's redundant, in the sense that I don't know if we'd have to visit B with two. I think we would. Okay, so if we consider, okay, so there is a cycle. So if we go this way, that correctly identifies it. But if we go this way, we'd still need to visit B again, because we wouldn't catch it. We would not catch the cycle just this way. So when we backtrack to here, we'd have C. Well, maybe we would actually. Oh, okay. So C at this point would have A, B, C in it. And then when we try to explore B, it would be in there. So that would be bad. All right, let me just try it like this and then see if there's any redundancies. So we'll basically have a DFS, but the twist would be every time we add to the stack, we'll also add a visited set. Okay, so that's 40 minutes. All right. Okay, so we'll have stack, which will be a list, and a tuple of within that list, which will be just any starting point. You just have to start from anywhere in the graph. Okay, I'll be right back. All right, I'm back. So obviously we have to start somewhere that has no prerequisites. So our graph is A, which is dependent on B. So at the end of our graph, maybe we could just identify starting points. Well, we have to identify every starting point in our graph, right? Because if we have like another node here, X, then if we have like Y, Z over here, Basically, we want to find every point in the graph that doesn't have any prerequisites and start there. So we'll say for course in graph, if graph of course and then also here too, I think what I want to say is if B not in graph, then we'll say graph of B equals empty list. So for instance, in this case where we have 0, 1 as A, B, we want our list actually to look like, 0, 1, but also 1, 0, or no, just 1, nothing. So it has no prerequisites. So if it's empty, then we want to, so we'll say, I guess we could just call our algorithm from there, starting points equals empty list, and then we'll say starting points dot append course. All right, so let me print graph. And starting points. Yeah, so it's going to be a longer episode today, which is fine. Okay, so here's our graph, and we should start at 1 because it has no prerequisites. What does that tell us if there's no starting point? So if there's no starting points, then we know obviously it's not possible as well. But that's not the only indicator, because we could have this, and there would be a starting point even though there's a cycle. So we can't just look at starting points. Okay. So now I guess I could have a function called DFS, which takes in a starting point. I guess I'll say start. And we want to, instead of doing this, we could probably just call DFS with course. Okay, so what we want to do here is say stack equals a list with the singular tuple. So remember, stack is going to be a list of tuples, or a stack of tuples, where the first element of the tuple is the course ID, and the second element of the tuple is a set of other course IDs, which if we visit them, we know there's a cycle. So we'll say start, and then we want a set with just start in it. So this would be like AA. Okay, and we'll say while, or maybe we could say, I'll call it the danger set, which will be a set of, because I also want to initialize this. It'll be a set with just start, and then here we'll put danger. Okay, so while stack we want to pop from the stack, and we'll say node and danger. So danger should be whatever we pops from that. And then we'll say for neighbor in graph of node. So for every neighbor, what do we want to do with the neighbor? We want to add it to the stack. So first of all, if neighbor is in danger, That's kind of funny. If our neighbor is in danger, we should help them. But in this context, we want to, like the whole problem, we know that there is a cycle. So is cycle equals true? I'll just say cycle equals true, and we'll return out of here. So this will exit the function. We'll say cycle. Okay, so I guess this function DFS can return, let's say, is cycle. So cycle equals false. Let's call it detect cycle like that. Cycle. So this function will return if there is a cycle. So cycle equals that. So if not cycle, so I guess we could say if not graph. So that's a starting point. And if we haven't found a cycle already, then we should explore it. So this is every course. If it's a starting point and we haven't found a cycle yet, so maybe what we could say instead is if there's a cycle, then return true. And then if we make it to the end, we can say return false. Or we could just say if this, return true. Or well, we should reverse the logic actually, because if there's a cycle, so yeah, if cycle means courses cannot be completed. So we have to reverse the logic there. So if there is a cycle, we actually want to return false in the context of this problem. Okay, so we need to know, so if we find a cycle, if we don't find a cycle, we'll keep going. Okay, so this should just return true if there's a cycle and return false if there's not. Okay, so if the neighbor is in the danger set, then we know there is a cycle. If the neighbor is not in the danger set, then we will append the tuple with our neighbor and the danger sets. But we want to add to the danger set, and it would be a copy, no? So we want a new set. So danger.add node. Well, we should honestly do that right at the beginning. Like this, right? Because we want to, if it visits itself as well, then So for neighbor in graph, so yeah, if it's connected to itself and it's, then we should return true because that should be in danger. So I think we want to return danger.copy. And then that copy will get reassigned to danger every time. If we get to the end of the stack without encountering that, then it should be false. Okay, so I'm not very confident that this will work right away. But I do want to run it and see if we get any errors here. So this builds the graph. So let's see what errors we get. DFS is not defined, that makes sense. So instead it is called detect cycle. Cycle. We also want to check yeah, so it's returning true even though it's not possible. So we can say valid start, or we could just say start exists equals false. And then if one of these is true, we'll say start exists equals true. And then here we'll say return start exists. Okay, let's see what errors we get. So I'm returning false, but it should be true. I'll just say here if length of graph, I guess I'll just say if not graph, return true. So if we have no dependencies, then we can just return true. Okay. So now I think we have a real actual test case. So I want to print popped from stack. And what I want to do is node equals this and danger equals this. Then I just want to trace this and see if this looks right. Okay, so I'm going to draw out this graph. Let me print graph. Okay, so 0 is dependent on 10. 10 has no dependencies. 3 is dependent on 18. 18 has no dependencies. 5 is dependent on itself. 6 is dependent on 11. So I output true for this, huh? 11 is dependent on 14. 14 has no dependencies. 13 is dependent on 1. 1 is dependent on nothing. 15 is dependent on 1 as well. 17 is dependent on 4. Okay, so this is the graph here. So the only cycle is this one. So let me just print. Let me print all the start positions. So start. So I just want to make sure it's correctly identifying all the start positions here. So 10, 18, 14, 1, 4. So 10, 18, 14, 1, 4. So it's not detecting 5 as a start position. So it's just never gonna explore that then. Similarly, if we had just an island like this, it also wouldn't explore that. So if the whole graph is dependent on each other, I mean, should I just DFS through from every node? This might, okay. So if I DFS from every node, because I guess that would, okay. So that would only, if I only look at valid starting positions, then I won't actually catch the bad ones. And I don't know if I need start exists anymore then. So we can, so not graph is true. So if the graph is empty, we want to return true. If it's not, so if it's empty, we want to return true. If it's, no, I think we just want to return graph. How do I just return if graph, like as a Boolean? I don't know how to do that. Like this? Okay, so graph here is empty, so it's returning false, but it should return true. So if length of graph, so if we did not detect a cycle, then we should return true, it's possible. Return true. Return true. Otherwise, we should return false like this, right? No, that doesn't. Oh, I guess we should do it earlier because I guess we're detecting. Well, this gets skipped, right? Well, start is never printed, so this function never gets called. And I don't return anywhere else, right? Okay, so the first time I return is in this function. Second time I return is in this function. So this is never getting called, so there's no way this ever prints. So let me see which one it is. I'm guessing it's false 2. Use test case. False 2. So what is the length of graph? Zero. So should this logic be reversed? Okay, so here there is a cycle. So it's possible. So it's not possible. Here it should mean that it is possible. It's also possible. So I think, can we just return true no matter what? Okay. All right, so yeah, even if there's no prereqs, then that just means it's true. Okay, so this is interesting. I don't know, I don't think this is how you're supposed to do a cycle detection, but I did get there eventually, and I did think about it myself. So if we think about the runtime, okay, so this is just like a depth first search. So I should be able to do it in one depth first search, but I'm not doing that. Well, I guess I am. Well, I was going to say here I'm doing like a depth first search for every... I want to retract my statement about me doing just one depth first search. Okay, so here I'm doing it for every component of the graph. So if there's no cycle, so if I have like A, B, C, D, E or something. So I'm calling it from A. I'm seeing if there is if there's one for A, and then I'm doing it for B, and then I'm doing it for C, and then I'm doing it for D, and then I'm doing it for E. So my time complexity is not within one depth first search. And my space complexity is fine, I think, actually. Well, I don't know if the space I don't know if the space complexity is good either, because we're copying a set for every element in the stack. So there's going to be a lot of redundancy here. So this is a very poor solution in terms of time and space complexity, for sure. But yeah, I'm glad I was able to still get it. So I think this is just one of those things that you should have memorized, is how to detect a cycle in the graph. So I'm definitely going to just look at the solution, see how to do it, and then probably revisit this problem. Yeah, but it was good. It's still good to try yourself, because now when I look at the solution, I'll kind of have that prerequisite knowledge going into it. So I'll remember it more. Okay. So I'll be back. I think I'm going to look at the solution and then come back and code it quickly. Hey everyone, I'm back. So I think I actually had the right idea. I think the only thing, so I looked at this solution and kind of traced it. So I think the only thing that I'm doing differently is I'm doing it iteratively. And because of that, I don't know if it's because of that, but I'm also copying the set, like the visited set, every time. Whereas in this solution, it's recursive, and then there's only one visiting set, and it's kind of like a backtracking pattern where they add to the set, DFS, and then remove the set, or remove the course from the set. But it's the same idea basically, where you have a visiting, like a danger set, like a visited set. I guess I could have just called it visited. I didn't know if I needed a separate one. So you have like a visited set, and you always kind of change it based on the node that you're currently at. And every time you backtrack, you remove that course. So yeah, I actually have the right idea, I think, at least according to this. I'll look at some other sources, because I thought there was a different way to detect cycles, but yeah, so that's today's video. So thanks for watching.